The title of this presentation is Asymmetric Generation and Detection of Surface Plasmon Polaritons Using Near-Field Apertured Probes, and is presented by Juan Merlo from the Physics and Astronomy Department at Vassar College. The outline of this presentation is the following. There is a short introduction to the near-field microscopy and the detection schemes used. Next, it is discussed the motivation of the present work, the experimental results, the conclusions of the presented results, and the acknowledgements. We start our brief review by defining the near-field optical microscope, or NSOM. It is an instrument able to measure the light-matter interactions in the close proximity of a sample surface. When a sample is illuminated with light, there is a response of the sample surface that is called the near field, and it is localized in a region that expands less than 1/2 of the excitation wavelength. Then, in order to sense this region, the NSOM uses a probe that can scatter this near field to be detected far away from the sample. Now, if the probe is scanned over the sample surface, it is possible to reconstruct the interactions in a two-dimensional image and related it with the topography of the sample. There are two kinds of near-field probes, apertured and apertureless. The apertured probes are essentially optical fibers coated with metallic films in such a way that a small aperture at the very end of the probe is generated. Such an aperture determines the resolution of the near-field mapping. The detection scheme in these probes is made far away from the sample by locating a photodetector at the end of the optical fiber. The apertureless, or scattering probes, are usually silicon AFM tips that are coated with a metal film to enhance their scattering cross-section. In these kinds of probes, the illumination and detection are made by free-space optical systems following a collinear path. Interestingly, the near-field microscope in scattering configuration has been used for the detection and analysis of surface plasmon polaritons in metallic surfaces and 2D materials. However, there is evidence that suggests the existence of important artifacts due to the interactions of different components of the electromagnetic field, not necessarily related to the surface plasmon polaritons fields. It means that far-field components are contributing to the overall measurement. In this particular case, two important works have been reported to the date. In both of them, the asymmetric generation and detection of surface plasmon polaritons in metallic surfaces is provided with an important contribution due to the far-field components. Actually, in the second work, a single crystal gold flake was used as the surface plasmon polaritons platform. In order to reduce the far-field contribution, it is necessary to use a different detection scheme. As such, in the present work, it is explored the asymmetric generation and detection of surface plasmon polaritons using apertured probes to determine if the contribution of the far-field components can be reduced significantly in the detection. Actually, in this work, it was used a scheme that was similar to the previously mentioned work, with comparison purposes. As mentioned before, we used a single crystal gold flake, with approximately 40 nanometers thickness. The thickness of the gold flakes was chosen in such a way that the surface support the propagation of surface plasmon polaritons, but avoiding important edge effects that have been reported previously. The figures are colored SEM pictures taken at 0 degrees to the left and 30 degrees to the right to determine the shape and thickness of the crystal, respectively. The experimental setup was composed of a laser source with wavelength of 660 nanometers with vertical polarization, a focusing lens with 20 centimeters focal length to bring the laser spot to a diameter of about 10 microns diameter at the very end of the probe, an APD as photodetector at the end of the probe, and the probe that had a diameter of about 300 nanometers. Finally, the incident angle, theta, was 32 degrees with respect to the vertical. It is important to mention that the scanning was performed by the sample, while the probe and the laser spot were fixed. All the experiments reported here have been acquired using the same experimental setup. Now let's focus our attention to the region where the interactions happened. In the scheme, the laser source impinges at the end of the probe. This generates a gap plasmon between the gold flake and the end of the probe. This gap plasmon launched surface plasmon polaritons radially, but only the surface plasmon with momentum that were perpendicular to the edges of the crystal, reflected back to the probe's position. This reflected field interfered with the upcoming plasmons and generated a set of interference patterns that were later detected by the probe. As mentioned before, the ENSOM has the ability to simultaneously explore the topography and near-field interactions on the sample surface. The figure shows the topography to the left and normalized near-field intensity to the right. From the topography, it is clear that the thickness of the crystal accomplished with the targeted thickness. Also, it is possible to clearly see the triangular shape of the crystal. The edges were called E1 through E3 for analysis purposes. In the case of the near-field intensity, the white arrow represents the direction of the in-plane component of the excitation field. It is possible to observe the interference patterns in the sample surface, as expected. Actually, it is important to notice that such an interference pattern has different components, coming from the edges of the crystal. However, it is clear that the patterns have different periodicities, as we expected due to the asymmetric illumination of the sample. Although the near-field images are a good indication of the nature of the interactions, it is always important to analyze the momentum space to determine the spatial components of the fields. Here is the normalized bidimensional fast Fourier transform of the near-field intensity. As it is clear, there are at least three dominant momentum components of the field that are called K1 through K3. This could not be surprising, as there are only three directions related to the crystal edges. However, it was found that some of these components are the results of the interference between two of the expected components. In order to analyze the components in a simpler way, the momentum components were mapped to a momentum space, where the horizontal axis represents the momentum in the x direction, while the vertical axis, the y direction. The black dots are localized at the same positions, with respect to the center, as in the bidimensional momentum space. First, it is possible to see that the position of the momentum of the in-plane component of the incident field is clearly identified as K0x. Then, it is also possible to see that the components K1 and K2 are simply the translation of the momentum of the surface plasmon in a flat surface, KSPP, by the in-plane component of the incident field, K0x. Moreover, the resultant components K1 and K2 are perpendicular to the edges E1 and E2. This means that the surface plasmon polaritons were efficiently launched at these edges. Next, the vector K3 is simply the sum of vector K1 and K2, meaning the interference between these two components. In addition, it is important to mention that the edge 3 did not generate surface plasmons polaritons, though scattered the in-plane component of the incident field, as it can be observed, as a low-frequency modulation generated at edge 3. This could be due to the shape of the crystal and the momentum mismatch on it. Finally, the fact that there were no evidence of far-field components as in the works presented before, we can conclude that the use of apertured probes avoided the generation of the artifacts presented in the scattering ENSOM. In summary, it has been demonstrated that the apertured near-fields probes can generate and detect asymmetric surface plasmon polaritons using similar conditions to those previously reported. Also, the analysis of the two-dimensional momentum space allowed the identification of the components that produce the observed interference pattern and their origin. Finally, this work allowed the reduction of the far-field contributions and allowed better imaging of the surface plasmons polaritons interactions in the surface of the gold crystal. The author acknowledges Vassar College for the startup funding, with number SD00057. Also, the author thanks Nanonics for the conditions provided in the purchase of the instrument used in this work. Thanks for your attention. For more information, please contact the author at this email address.